Coming up in this edition, you don't need to be a rocket scientist to know that America's space program is a very costly venture, but you do have to be one to work here. NASA's Sounding Rocket program lets rocketeers young and old test their own low-cost, high-risk spacecraft. Learn from your mistakes wasn't quite the catch cry for the original Gemini training sessions or space missions, but it should have been. The lessons learned in the early days of spacewalks and reconnaissance flights are still in practice today. And journey 4.5 billion years back to when Mars was being formed from the gas and dust of the solar nebula. By discovering its origins, we better understand just how unique the red planet really is. But first, to south-central New Mexico, home to the White Sands Missile Range, which has been testing scientific payloads since the 1950s. A group of veteran rocketeers from NASA's Wallops Flight Facility in Virginia routinely visit White Sands to assemble and launch small scientific payloads into space. NASA's Sounding Rocket program was set up to be a low-cost, high-risk operation, where the rocketeers would take a few more chances in order to get the speed and the turnaround time that the experimenters were looking for. Aerospace engineer Bob Spagnola is in charge of assembling the rocket. Multiple segments that control vehicle ignition, guidance, telemetry, recovery, plus an X-ray telescope all fit together to make up an 18-foot payload. Everything is tested before assembly on a shaker device to duplicate the vibrations and rigors of launch. Simulations are used to activate the payload's protective door, revealing the telescope sensors. The ability to go into space provides sounding rockets with their unique view. Clear of the distorting effects of the Earth's atmosphere, they escape the bounds of Earth for just a few minutes. That's long enough for University of Colorado student Dennis Gallagher. He designed the mission to collect information on a binary star. The twin star, called Scorpius X1, has an intense gravitational field which heats matter to millions of degrees. The Sounding Rocket's telescope is able to read X-rays coming from it, providing data on the star's physical makeup. Fully assembled, the half-ton of instruments are stacked upon 2 tons of rocket motors, and the count begins. This is always a tense time for mission controllers, right until a successful launch. Throughout a flight, scientists take data for 7 minutes before the payload starts plummeting back to Earth. It lands downrange, 50 miles from where it was launched. At first light, helicopters deploy for the recovery. Today, the crew is lucky. Payload is intact with barely a scratch on it. In no time at all, it's unbolted into manageable sections for the flight back to the installation. After changes and improvements, most payloads end up flying over and over again. It's a low-risk way to launch experiments into space quickly and at minimal cost. On the first 8 manned space flights into space, the job of re-entry was always left up to the command pilot. On the final 2 missions, the computer alone automatically controlled the descent, with the pilot ready to take over should the need arise. On the first 3 manned flights, Gemini 3 through 5, landing accuracy was only 57 nautical miles from the planned impact point. This distance soon improved. When Gemini 6-8 landed, it was within just 7 nautical miles of the planned impact point. Gemini 8, despite an orbital abort, landed within 1.1 nautical miles of the planned secondary impact point. Although it came down 8,000 miles away from the primary target area, it achieved the second-best landing accuracy ever recorded. Tom Stafford shaved that distance to 0.4 of a mile in Gemini 9A, establishing a remarkable record. Overall, the average missed distance for the last 7 flights was 3.6 nautical miles. Statistics such as these were vital in planning the lunar missions. Crews returned from the moon at around 25,000 miles an hour. To land safely within a 3,300-mile footprint, they needed to hit a re-entry corridor within 2 degrees of the planned flight path. Spacewalks too have improved over time. This 22-minute walk during the Gemini 4 mission went smoothly, without too much disorientation felt by the astronaut, but it was hardly graceful by today's standards. 4 additional EVA flights were flown as Gemini progressed from relatively uncomplicated spacewalking to meaningful spacework by an EVA pilot. On 3 flights, Gemini 9A, 10 and 11, the pilot faced problems of body control and workload. 2 answers evolved: a new underwater training program for crews and the increased use of body restraints during work sessions. Astronaut Cernan had 9 pieces of body restraint equipment during his Gemini 9A flight. The space agency progressively developed and refined restraint equipment till 44 pieces were flown on Gemini 12. Underwater simulation of zero-gravity conditions was also added to the training schedule of both the prime and backup crews of Gemini 12. This gave them a greater continuity of training that is possible in the parabola of aircraft flight. Buzz Aldrin put to work the experience gained from 4 flights and underwater training. He completed 19 tasks in a 2-hour, 19-minute EVA. He performed such fundamental space work as activating an experiment, tightening and loosening bolts with an Apollo torque wrench, making electrical connections, and cleaning up his work area. In all, Gemini amassed 12 hours and 22 minutes of EVA experience. It included spacewalking, stand-up EVA for photography, and space work. Gemini EVA gave us the assurance that man can work and explore in the vacuum of space, whether he be on the moon or on orbiting space stations. By the time the Apollo missions were ready for launch, a trained staff of highly experienced mission controllers were already in place too, all thanks to the earlier Gemini flights. The original Cape Kennedy staff were responsible for no less than 12 successful Gemini missions. In addition, they demonstrated a dual launch capability, while 4 Agena target vehicles and 1 augmented target docking adapter were launched successfully. Recovery personnel from the Department of Defense and NASA reduced the number of recovery ships by 50% between Gemini 4 and Gemini 12. At the same time, they increased spacecraft retrieval efficiency by 50%. The record of the flight crews is of course better known. By the time the last spacecraft splashed down, Gemini had logged 1,940 man-hours, almost 40 times as great as Mercury. Over 2,400 synoptic and terrain photographs were taken. 2,000 of these supplied useful information to scientists. The aerial mapping potential of manned flights was best illustrated by the Gemini 9A flight over Peru. In one pass, Gemini 9A mapped 8% of the country, and it took just 3 minutes. These photographs were supplied to the Peruvian government. Commercial uses have been many and varied. This Texas coastal area shows the larval distribution of shrimp. One commercial fisherman reported that he learned more by studying this photograph than by fishing the Gulf for over 25 years. Weather photographs have been equally rewarding, enabling us to study the vortex of storms and build-up of storm regions in successive photo passes. Gemini also photographed sources of air pollution over cities, channels of rivers, and the flow of jet streams. The International Affairs Office of NASA makes available such information to interested scientists of all countries. Those 52 experiments, the 1,940 man-hours of the 12 Gemini and their main objectives are now well and truly over. But they've given us the experience and confidence to tackle all the future goals of manned spaceflight. To land for the first time on the moon, explore it, and return to Earth. To acquire new scientific knowledge in orbital workshops, and to reach out towards interplanetary exploration. later mappings of the planet displayed light and dark regions, identified incorrectly as continents and oceans. The land masses as red as the sandstone areas on Earth, and the water a greenish blue. In 1877, Italian astronomer Giovanni Schiaparelli discovered what he called canala, or canals, resembling, he said, the finest threads of a spider's web drawn across the disk. In America, Percival Lowell founded an observatory to study these Martian features. Massive irrigation systems, he called them, designed to carry water from the melting ice caps to the major centers of a dying civilization. Science fiction writers populated the city with terrible creatures of enormous size and skills beyond Earthman's dreams. In the 1960s, 3 Mariner spacecraft flew by Mars and photographed about 10% of the surface. Gone were the canals, gone were the cities, and gone were the brilliant but sinister Martians. The photographs revealed a cratered landscape much like the Moon, waterless and apparently hostile to life. But in 1971, the Mariner 9 spacecraft orbited Mars and transmitted more than 7,000 photographs of the planet to Earth. The extensive mapping revealed a new and unexpected world. The southern hemisphere, seen by earlier spacecraft, was flattened and gouged by the impact of meteorites, while the northern hemisphere was a vast plain with few craters, and rising from it, a great dome called Tharsis, topped by giant volcanoes. The plateau that joins the two hemispheres is cut by a vast and deep canyon, and by channels with a characteristic pattern of stream beds on Earth. Some of the channels suggested that water may once have flowed on Mars, and thus life might have evolved and possibly adapted to Mars' changing conditions. And then, in 1975, 2 Viking spacecraft were launched, each of which was programmed to land a robot on the Martian surface. One of its principal objectives was to test for the presence or absence of living organisms. A communication system linked the spacecraft to the Mission Controlling and Computing Center in Pasadena, California. On June 19, 1976, the first Viking arrived in the vicinity of Mars after a year-long journey of more than 400 million miles. Once in orbit, its cameras began a detailed examination in order to locate a landing area. Imaging teams on Earth scanned some 800 photographs, covering a territory about the size of Texas. The chosen landing site was a flat expanse with a few impact craters, one of the lowest regions on the surface. On July 20, 1976, flight controllers ordered the lander to separate from the orbit. Because of the great distance from Earth, the signal traveling at the speed of light, 186,000 miles per second, took 19 minutes to reach the spacecraft. This necessitated a completely automated onboard system for carrying out the landing maneuver. During the lander's descent, its instruments analyzed the properties of the thin Martian atmosphere. As the lander floated closer and closer towards the planet's surface, the controllers held their breath. Their entire mission was about to come to fruition or disappear under eons of Martian dust. At 600 feet, men of science and physics could do no more than cross their fingers and hope. The the lander continued its controlled landing at a rate of 73 feet per second, following a smooth parachute separation. Finally, success. Just 25 seconds after landing, one of the two onboard cameras was initiated and began scanning the first picture of the Martian surface. Soon, controllers were staring at a long panoramic view which covered 300 degrees and extended from the lander to the horizon. It disclosed a sector of the basin called Pryce-Panica, covered with sand and dust and littered with rocks. The following day, Viking sent back the first colored picture. A fine reddish-brown dust covered the ground. The sky was a light tint of the same color due to the particles of dust suspended in the air. 45 days after these historic events, Viking 2 landed in an area 4,600 miles northwest of Viking 1's landing site, a vast plain littered with rocks resembling those on Earth, produced by volcanic processes or by meteorite impact. While the lander conducted experiments on the surface, the orbiter swinging around the planet measured variations in the moisture and temperature and took high-resolution photographs of the Martian terrain. $4.5 billion years ago, the planets were formed from the gas and dust of the solar nebula. The formation of a planet, heat is released and becomes embedded in the growing mass. Because the heat can't escape as rapidly as the mass is growing, a point is eventually reached where the interior melts. On Mars, the heavier materials sank towards the center, while the lighter material rose to form an icy crust on much of the surface. A later stage may have occurred when molten rock intruded into the crust and melted the ice, causing a slurry of water and rock and dust to flow across the surface. Some observers believe that such a process may have been the cause of the major channels which we see on the surface of Mars today. Others believe that in the planet's first billion years, the atmosphere may have been warm and dense enough for rain to fall and rivers to flow. Gradually, the original big, wet and warm blanket of the atmosphere evolved into the thin, dry, carbon dioxide-filled atmosphere we find there today. Because of Mars' low atmospheric pressure and low temperatures, water can't exist in liquid form. It must either freeze or evaporate. But while there are no oceans or rivers on Mars, there's more water in total than anyone had expected. The residual polar cap in the north, which remains after the hottest part of the northern summer, is a mixture of ice and dust. And the measurements of the seasonal behavior of water vapor over the planet suggest that there is a vast reservoir of ice beneath the surface. In fact, the residual polar cap could be compared to the tip of an iceberg, protruding from a sea of rocks. At lower latitudes, a water vapor condenses to form clouds that hang high in the atmosphere, or swirl around the tops of Martian volcanoes. Further south in the canyons and valleys, there is frequently an ice haze, seen to form and evaporate in the early hours of the morning as the sun warms the atmosphere. On Earth, the oceans, heat and moisture, and the air currents over land masses interact to produce complex weather patterns. On Mars, because of the absence of large bodies of water or massive cloud cover, the weather doesn't vary much from day to day. But in the early summer, the heating of dust particles in the air generates violent dust storms in the lower regions of the planet. Driven by winds that reach up to 150 miles an hour, they can blanket the entire planet in a few days. And we'll have more on this amazing planet in our next edition of Above and Beyond.